Hello, this is Brother Cromer from the Math Department, and I'll be covering in this video is Lesson 24 dealing with inference for bivariate data. And so here's the outline for Lesson 24. First, I'll introduce or have an intro of the inference or to inference in regression. Then I'll talk about the requirements for linear regression. We need to do those before we get to hypothesis testing and confidence intervals. And we'll look at 3 different requirements that we could check. And then we get to hypothesis testing and then confidence intervals. So first of all, here's the intro to doing inference for linear regression. This is basically talking about parameters and statistics. So a parameter is a measure of the population that is typically unknown, but we like to estimate. So mu is the population mean, p is the population proportion, and now we have beta naught and beta 1. Beta naught is our true y-intercept, and beta 1 is our true linear regression slope. So statistic is a measure from the sample, and the statistic is used to measure the unknown parameters. So we have our sample mean x bar, p hat, which is our sample proportion. Now we have b naught, which is our sample y-intercept, and b1, excuse me, which is our sample slope. And so x bar estimates mu, p hat estimates p, b naught estimates beta naught for our true y-intercept, and b1 estimates beta 1, which is our true regression slope. And so the true regression equation is y is equal to beta naught plus beta 1 times x plus epsilon, where beta 1 and beta naught and beta 1 are parameters, and epsilon is a normal random variable. Okay. So now what I want to talk about is the requirements for a linear regression. So there's five requirements. First of all, there is the linear relationship, and so when we look to see the requirement of linear relationship holds, we'll look at 2 plots, a scatter plot and a residual plot. With a scatter plot, we hope to see a hot dog shape, and with the residual plot, we hope to see no patterns in the residuals. The second requirement is a normal error term, and so we'll look at a QQ plot of residuals. So we'll put the residuals in a QQ plot to see if the points in the QQ plot are close to the line. If they are, then we can assume a normal error term. The third requirement is constant variance. Okay, and we look at a residual plot as well. And when we look at this residual plot, we hope to see no megaphone shape in the residuals. Now the last 2 requirements, x's are known constants and observations are independent. We cannot check directly. However, what we hope to see is that the x should be measured accurately and precisely for the 4th requirement. And for the 5th requirement, knowing the values of one of the y's tells you nothing about the other points. So either sample or independent. Okay. So now let's talk about linear relationship. Okay. So first of all, with the crocodile data. So I used the crocodile data as well as the manatee data for lesson 23. I'll do it again for lesson 24. With the crocodile data, we wanted to predict the body length based off the head length, going back to the supercroc video where they wanted to predict the body length because they found a skull of supercroc, a big skull, so they wanted to predict the body length of supercroc. So if we created a scatter plot, and this is a pretty good fit. Now it says the data has a hot dog shape. Now what it's meant by that is that imagine if you will the line represents if you're looking on top of a hot dog, if you will, looking over the hot dog, you could see that the line represents, if you will, the meat of the hot dog, and then the dots around it represent the bun. Now this sets to be that the data has a hot dog shape. Okay. Now the residual plot on the right side. Now notice the residual plot compared to the scatter plot. The scatter plot has the explanatory variable on the x-axis and the response variable on the y-axis. But with the residual plot, we have the explanatory variable still on the axis, but the x-axis, but the residuals on the y-axis. And so when we do that, what happens is that it moves the scatter plot, or it shifts the scatter plot to where the line here is horizontal. Okay, and we can take a pretty good look as well to see if there's a pattern. And so in this case, there isn't a pattern when we look at the residuals. Now, what does it mean whether or not there's a pattern? Well, I have a couple of examples here on the next page where this is if you see that there is no pattern, that it looks to be a bunch of dots that are centered around the middle of the residual plot. Now, if we see something like this, then that is definitely a pattern. This tells us that perhaps we do not, and all likely we do not have a linear relationship. Okay. So here's another example of checking the requirements, the manatee data, where we predict manatee killed based off the number of powerboats registered. So the scatter plot on the left here, it looks also to have a hot dog shape here, where the line here represents the hot dog, the meat, and then the points represent the bun, and it looks like that there is a linear relationship, and it's confirmed by our residual plot here, where the x-axis is the power boats. That's our explanatory variable, and our unstandardized variable, our unstandardized residuals is on the y-axis, and it looks like that there is no pattern when we look at our residual plot. Okay, now, what I'd like to do is now talk about the normal error term requirement, and we look at QQ plots of the residuals when we do that. And so points in the QQ plot are close to the line that's what we hope to see when we look at the QQ plot, to check to see the requirement of normal error term is met. So here is an example of the crocodile data where we put the residuals into a QQ plot, and we notice here for the most part the dots are at or close to the line, except for this one outlier. But it looks like the error term, the points appear to be close to the line, so the error term appears to be normal. Okay. Now here's a second example with the manatee data, predicting manatee killed based off the number of powerboats registered. Now there's a few points here on the outside. There's perhaps a few outliers here, but it looks like for the most part that the error term appears to be normal. Okay. So checking the requirement for a normal error term, it looks like the requirement is met. Okay. So then finally, the last requirement is constant variance. So we're going to go to a residual plot again. We look to see that there is no megaphone shape. Now here's going back to the crocodile data. So this is to predict body length based off of head length. Okay, and we do the residual plot where the x variable is the head length and the y variable is the residuals. Now here's what I mean by megaphone shape. If the variance from the center starts out small but then it fans out, and that's where it would be a megaphone shape. Now in this case, it doesn't look to be a megaphone shape. It seems to be across the board. The variance is about the same. But here's what it looks like when you have a megaphone shape. It starts off small on the left, and then it fans out to where you have a megaphone. If we have that, then we cannot assume constant variance. Okay. Now here, the next example with the manatee data, we predicting manatee killed based off the number of powerboats registered. So on this residual plot, the x-axis we have powerboats and the y-axis is residuals. You could say that perhaps it starts off small and it fans out, and you could say that there is, in fact, I say here there's a slight megaphone. But in my opinion, it's not big enough to say that we cannot assume constant variance. So I'm going to assume that the requirement is met. Okay, and so that concludes part 1 of the lesson 24 video. When we get to part 2, I will cover hypothesis testing and confidence intervals.